All right, let's finish section 9.2 with one more application of partial derivatives. All right, I really like example 8 here because it's a real world phenomenon that you might have heard of. So in 1941, explorers Paul Sippel and Charles Passel discovered that the amount of heat lost when an object is exposed to cold air depends on both the temperature of the air and the velocity of the wind. They developed the wind chill index as a way to measure the danger of frostbite while doing outdoor activities. The wind chill can be calculated with the formula W of V comma T equals this big stuff. And who knows how they came up with this, okay? But apparently it accurately predicts the amount of heat lost and pretty much what the temperature feels like. Okay, where V is the wind speed in miles per hour and T is the temperature in Fahrenheit for wind speeds between 4 and 45. Okay, and so there's the source. This is a real formula developed by these people in 1941. And maybe you've heard of this before. If you've got a certain temperature outside, but it's really windy, it feels a lot colder than the temperature would read on a thermometer. And that definitely makes it a bigger threat for you to get colder, get frostbite for a temperature that might not have seemed all that outrageous until you factor in that wind speed. Okay, so let's dive right in here. Find the wind chill for a wind speed of 20 miles per hour and temperature of 10. Okay, so no partial derivatives or anything yet. We're literally just plugging in 20 for V and 10 for T into this function. And let's see what the result is. Okay, so I'll write that out. We have W of, so the wind speed is 20, or wind velocity, I suppose, 20 miles per hour. That's why the variable is a V, and a temperature of 10. Okay, so here we go. It's just gonna be real quick, 91.4 minus the 10.45 plus 6.69 square root of 20 for V minus 0.447 times 20 for V times 91.4 minus 10 for T. Be a little careful with your fraction here. The divide by 22 is only over that stuff. It's not over, or is only under all of that stuff. It's not under the 91.4. Okay, that first 91.4 over there. Okay, so let's type this in. 91.4 minus parentheses 10.45 plus 6.69 times the square root of 20 minus 0.447 times 20 times 91.4 minus 10. And then that stuff is all over 22. Okay, so I got approximately negative 24.88. I'll round to 3 decimal places. And this will be degrees Fahrenheit for the wind chill. Okay, so kind of interesting there, okay, to really think about that. If the actual temperature is 10 degrees and you've got this 20 mile per hour wind, it actually is effectively like it's negative, almost negative 25 degrees. So that's a significant difference in how cold it feels when you factor in that wind. Okay, interesting stuff. I think it's totally fascinating. So let's get into the partial derivative stuff. Let's find and interpret the partial derivative of the wind chill function with respect to V and the partial derivative of the wind chill function with respect to T. And we'll evaluate it at 20, 10 both times. And then we'll interpret that. And of course, we'll do our nice long sentence to really focus in on what that means in the context of the problem. Okay, so let's just do each of these separately. So I'll go ahead and just write it out as W V, and before plugging in the 20 and the 10, let's just find the derivative itself. And then we'll plug in the 20 and the 10 after we're done. Okay, so here's where it's a little bit tricky because we want to see if maybe we can apply some of those techniques we used in the previous example where we think about a constant multiple to make our life a little bit easier so it doesn't have to be any kind of a big nasty product rule of some kind. So for this partial derivative, we're holding t as a constant because we're doing the derivative with respect to v. So looking at this whole function here, first of all, this 91.4 in the front, that's not a constant multiple because it's 91.4 and then minus the rest of the stuff. So when we go through and take the derivative, that thing's just going to turn into a 0. Okay, so I can pretty much just ignore that 91.4 when we're taking the derivative. Okay, but throughout the rest of this stuff, notice that the v, which is what we're considering as the variable right now, is only inside this first big set of parentheses. And then this 91.4 minus t, all of that is going to be a constant when we're doing the derivative with respect to v. And then this all divide by 22, that divide by 22 can also be considered part of our constant multiple. So I'm going to get a little bit fancy and consider all of that stuff. I don't know what that number would be, but it's just a constant multiple. And so I'm going to write that in the front, but I also need to be careful. So as I go through now, I'm taking the derivative. So the 91.4 in the front right there is gone. That's a 0, but there's still this negative sign there. So that's part of the constant multiple. So I'll go ahead and include that negative sign, and then I'll have this 91.4 minus t, and I'm going to include that divide by 22, all as the constant multiple. Okay? And then that first 91.4, the derivative of that is just 0. Okay, so constant multiple times, and now we do the derivative of all of that stuff in there with respect to v. So let's go through and take the derivative of each piece. So the derivative of the 10.45, that is 0 plus, okay, so that's square root v. V is being considered as the variable here, so you might want to try to think of it as v to the 1/2 power and just use the power rule there. So the power rule says it will multiply the 1/2 down in front. So 1/2 times this 6.69 number, and then it's going to be v to the subtract 1 from the power. So negative 1/2. Okay, and then moving right along, the derivative of 0.447 v, where v is the variable, is just going to be the constant. So there's the minus and 0.447 without the variable now. Okay, let's clean this up a little bit. W, v, v comma t equals. Okay, so let's see, for not really any reason, it might look a little bit cleaner if we distribute that negative in there, because then it would be a positive t, and I can write that in the front, and then it'll be a negative on the 91.4, and so I can write it as t minus 91.4, just to look a little bit cleaner. Okay, and then right here, there's that 0, but then we have 1/2 times the 6.69. Okay, so just typing that in, 3.345. And since that v is to the negative 1/2, let's go ahead and make a fraction out of it and put it in the denominator as v to the 1/2 down there. And I'll put it in that radical notation. And then minus the 0.447. Okay, so that's probably clean enough to write that derivative there. So far, so good? Okay, so let's go ahead and do the partial derivative with respect to v, evaluated at, and we wanted 20, 10. Okay, so we're plugging in 20 for v and 10 for t. So here we go, 10 minus 91.4 over 22 times 3.345 over square root of 20 minus 0.447. Okay, let's type this in and see what we get. 10 minus 91.4, all that divided by 22, and then times 3.345 divided by square root 20 minus 0.447. Multiplying this all out, I'll go to several decimal places here. It's negative 1.113 5, 6, 9. So I think I'll go 5, 7. Okay, pay attention to how you're being asked to round because my calculator is displaying several more places after that, but I think that's good enough. Okay, so that is the partial derivative of the wind chill function with respect to v evaluated at 20, 10. Okay, now the interpretation. So what did we just do? And so I'm going to make a sentence out of this. So we actually, while we're doing the partial derivative with respect to v, we're holding temperature constant. And since we're evaluating the temperature, the real temperature at 10 degrees, let's actually mention that. So let's say while, so this is the interpretation. While holding the temperature constant at 10 degrees Fahrenheit. Okay, what? The rate of change of the wind chill index is changing by this number that we found. So this negative number. And since it came out negative, we can actually write in our sentence that the rate of change is decreasing. Okay, so while holding the temperature constant at 10 degrees Fahrenheit, the wind chill decreases. And watch out for that. If you get a negative rate, watch out for the wording. If you see that word decreases, then that's including the negative in the sentence. Okay, so I'll go ahead and highlight that. The wind chill decreases approximately. And since I use that word decreases, I'm going to use a positive number for this answer we got. It decreases approximately 1.11357 degrees Fahrenheit when, okay, so the wind velocity, since this is the derivative with respect to the velocity, the speed of the wind, when the wind velocity does that thing where we talk about it changes by 1 unit. Okay, so when the wind velocity increases by 1 mile per hour. You can get a little bit more specific, and it's from, since we did a 20 in there, from 20 miles per hour to 21 mile per hour. Okay, so there we go. That is the interpretation. So we hold temperature constant at 10 degrees. The wind chill decreases approximately by that many degrees when the wind velocity increases. And that should make sense. As the wind velocity goes up, the perceived temperature goes down. And that's the rate at which it goes down. Okay, let's try the next one now. T, so the derivative with respect to t evaluated at the same numbers. Okay, so let's do the derivative over again. I have this extra blank page already available because I knew it would take a little bit of space. So let's write down WT VT. And again, we want to do a little bit of maneuvering here so that we can take the derivative in a nice way. So going back up to our function, let's see, I'm going to erase some of this stuff that I wrote here. This time, when we're taking the derivative with respect to t, the v stuff is the constant. So as I go through here, this 91.4, again, if I'm taking the derivative, that just turns into a 0. So the only thing we need to think about is there's this negative, and then if we're pretending or if we're holding v as a constant, then notice that all of this stuff is just a constant multiple of the 91.4 minus t. Okay, so that's pretty nice. All of that stuff is a constant multiple. So I'm going to go ahead and write that down. So as we're going through, we're taking the derivative now with respect to t. This first 91.4, that just turns into a 0. And then there's going to be that constant multiple. So we have the negative, and it's going to be all of that stuff. And so the 10.45, just write all that down. The 10.45 plus the 6.69 square root v, and we're just holding v as a constant, minus 0.447 v again. And I'm kind of bundling all of this with the divide by 22 part. And then it's times now the derivative of this stuff, because we're letting t be the variable. So the derivative of that stuff inside there. So we just go 91.4. What's the derivative of 91.4? 0. And then minus. And then what's the derivative of just t? Well, if t is the variable, it's just a -1. Okay, it's just going to be whatever is the constant in front of it. And so if it's just minus t, it's just -1. Okay, that's the derivative. So that was actually a little bit easy to actually perform the derivative, but to do that setup with paying attention to which pieces are constant multiples and which pieces are treated as variables, a little bit tricky and a little bit fancy, but that derivative came out fairly nice because now we can just write it as w of t of v of t equals. And so not really a whole lot we can do to clean this up except for realizing that, and it was very important that we had this extra -1 show up over here, because this -1, and I can apply it to that negative in the front right there as well to make it become a positive, okay? Just negative times negative right there. So let's just write it as now without that negative in front, 10.45 plus 6.69 square root v minus 0.447 v all over 22. Okay, if it trips you out a little bit that I'm putting the over 22 on this stuff, well, we can always just think of as like ×1, and then the 22 would be on the bottom of everything anyways, if I put the other stuff like all over 1. So that's kind of the nice little trick where we can get that divide by 22 just kind of grouped with the part that we want to treat like a constant multiple. Okay, so there it is. That's the derivative of the wind chill function with respect to t. So now we just want to evaluate at 20 miles per hour and 10 degrees. So let's go ahead and plug that in, and notice that the only variable involved now is that v. Okay, as we're plugging this in, and v, like when we're doing this with respect to t, v wasn't even a variable when we were doing the derivative, but now since v shows up in the derivative here, we can evaluate it by plugging in 20 for v, and then there's no t anywhere for the 10. But let's go ahead and just evaluate it. We have 10.45 plus 6.69 times the square root of 20 minus 0.447 times 20 all over 22. Okay, let's type this in and see what we get. And then the all-important interpretation. 10.45 plus 6.69 times the square root of 20 minus 0.447 times 20, and then all over 22. And so I'll go a few decimal places, 1.42857. So let's just go 86. So that is the number that we get. And now the all-important interpretation. What does that number mean based on what we plugged in and what partial derivative that we just took? So what do we do here? This time we're holding wind velocity as the constant, right? Because this is a derivative with respect to t, with respect to temperature. So let's start our interpretation sentence. While holding the wind velocity constant at, okay, and we plugged in 20 for V, so at 20 miles per hour. Okay, what do we just find? Okay, so the rate of change of that wind chill function is this positive number. So the wind chill increases by approximately this many degrees when the actual temperature increases by 1 unit. Okay, so let's, and the actual temperature, the units are degrees Fahrenheit. We can get a little bit more specific. Okay, so while holding the wind velocity constant at 20 miles per hour, the wind chill index or the wind chill function increases, the wind chill index increases approximately that number, 1.4286, and it'll be degrees Fahrenheit. When the actual temperature increases by okay, 1 unit, okay? And so since the units are degrees Fahrenheit, we'll say by 1 degrees Fahrenheit. And in parentheses, we can get a little bit more specific about the specific range that we're thinking about here. Increases by 1 degrees Fahrenheit. Well, this is the 10 right here. So we can say, remember, that's like that from A to A plus 1, or from B to B plus 1, or however we wrote it in the past. So it's from 10 degrees to 10 plus 1 degrees, or 11 degrees. So that would be our interpretation of what happened there. And so this should also make sense if we just assume that the wind velocity is just constant at 20 miles per hour. If the actual temperature goes up, then the wind chill is also going to be going up. But it's kind of interesting the different rates that things are going up based on certain things being held constant and certain increases of other things. All kinds of amazing interpretations for partial derivatives. Okay, so that finishes off section 9.2. I hope you had a little bit of fun with the partial derivatives and kind of got inspired with how much calculus can really do in all kinds of applications. All right, so that finishes off section 9.2. Hope you have a good day.